Think for a moment about the sheer scale of our Milky Way galaxy. Billions upon billions of stars stretching across, well, just unfathomable distances.
It's almost impossible to truly picture its immensity.
Right. And the total amount of stuff in it. And here's the real kicker. We're living inside it. So you might wonder, how on earth do scientists even begin to weigh something so gigantic from within?
That's the central puzzle, isn't it? It's like trying to weigh an airplane while you're a passenger on board.
Ah, yeah, good analogy.
But one of the most clever techniques we've developed to tackle this cosmic weight problem is by observing globular clusters.
Globular clusters, these incredibly old and tightly packed groups of stars that orbit our galaxy. Okay, let's unpack this. How do these massive star swarms help us understand the Milky Way's total mass?
Essentially, they act as miniature galaxies orbiting our own. Their paths through space are governed by the gravitational pull of everything within the Milky Way, including the mysterious dark matter. By meticulously tracking their movements, we can create a sort of map of the distribution of mass that's influencing them.
I see.
And understanding this mass distribution is absolutely crucial for figuring out how our galaxy originally formed and, how it continues to evolve over billions of years.
So this deep dive is like getting a fast-track pass to some truly cutting-edge galactic detective work. We're going to explore how scientists are using these ancient star groups as cosmic clues to uncover the hidden structure of our galactic home.
Yeah, should be some real aha
I can already feel those coming.
Precisely. We'll be looking at how our understanding has grown over the decades, from painstaking measurements using old photographic plates
Wow.
to the amazing precision we now have with modern space missions like Gaia. It's a fascinating story of persistent scientific curiosity.
Right. So our mission today is to extract the most important knowledge about how the movements of these globular clusters are helping us determine the Milky Way's mass and its overall shape. Let's dive in, shall we?
Absolutely. The initial efforts to study how globular clusters move were truly groundbreaking. Way back before space telescopes, astronomers had to rely on things like photographic plates
Right, you mentioned those.
to measure the incredibly subtle proper motions, their tiny shift in position across the sky over very long periods. It was a slow and incredibly detailed process.
Imagine trying to track something so incredibly far away using technology from, what, over a century ago? That sounds unbelievably difficult.
It was, really tough. But even with those limitations, by the 1980s, researchers had managed to identify a general pattern in the orbits of over 60 globular clusters.
Okay, so some progress.
Yes, and they also noticed something intriguing. The velocity dispersion, basically, how much the speeds of the clusters varied within the group seemed to increase the farther they were from the center of the galaxy.
Hmm.
And perhaps most significantly, they were starting to map out the galactic rotation curve, the speed at which stars orbit at different distances from the center, which hinted at the existence of a massive, extended halo made up of, well, something we couldn't see.
Something mysterious, I gather.
Indeed, the evidence strongly suggested that there was a lot more mass present than we could account for just by looking at the visible stars and gas. Then came the 1990s, which brought some truly exciting discoveries.
Tell me about it. What happened then?
Well, one key development was Lyndon Bell's work in 1995, where he identified streams of globular clusters.
Streams, like trails of stars.
Exactly. The really important insight here was that these streams were likely the remnants of smaller satellite galaxies that had been torn apart and merged with the Milky Way over vast stretches of time.
Ah,
Think of it like finding faint trails of milk swirling in your coffee long after it's been stirred.
okay, yeah.
They even connected specific streams to known dwarf galaxies, like the Magellanic Clouds, Fornax, and the Sagittarius Dwarf.
Yeah. Wow, so the orbits of these clusters were actually telling tales of ancient galactic mergers. That's a wild thought.
It really is.
So, the fact that we see these streams of stars today is direct evidence of these ancient galactic mergers. That's a powerful way to look at the history of our galaxy.
It is. Lyndon Bell also predicted that 22 specific clusters should exhibit particularly high proper motions, which was something that future, more precise observations could test.
A prediction to check later. Got it.
Right. So if we fast forward to around the year 2000, when the European Space Agency was in the planning stages for the Gaia mission, what was our best understanding of the Milky Way's mass at that point?
Based on our sources, it sounds like our knowledge was, well, pretty uncertain, to say the least.
Uncertain is putting it mildly.
Imagine trying to weigh an elephant and your scale gives you an answer anywhere between a small car and a large truck. That's kind of the level of uncertainty we were dealing with.
That's a very apt analogy, yeah. The best estimates of the total mass of the Milky Way back then relied on the motions of only 27 objects located more than 20 kiloparsecs away. That's over 65,000 light years.
Only 27? That doesn't seem like many.
Not at all, for something so huge. The total mass was estimated to be somewhere in the range of 2.3 plus 3.9 minus 1.6 times 10 to the power of 12 solar masses.
Whoa, that's a massive range.
It is. That huge range of uncertainty really highlights how poorly we understood things. And the estimated mass within 50 kiloparsecs also had significant error margins. The extent of the Milky Way's halo, that enormous diffuse region surrounding the visible galaxy, was one of the most poorly defined characteristics of our own galactic home.
So we had a rough idea it was big, but the how big part was a massive unknown. Now, our sources mentioned the Hipparcos mission. How did that contribute, and what were its limitations for globular clusters specifically?
Hipparcos. It was a truly revolutionary mission for precisely measuring the positions and motions of stars, definitely. However, its instruments weren't sensitive enough to directly observe individual stars within globular clusters because they were generally just too faint.
Okay, so it couldn't see into the clusters?
Not the faint stars, no.
Yeah.
But the scientists behind the mission were quite ingenious. They made a deliberate effort to include bright reference stars that happened to be located nearby a few selected globular clusters in the Hipparcos observing program.
Okay, so these nearby bright stars acted as fixed points of reference, like celestial signposts.
Exactly. By precisely measuring the positions and motions of these reference stars, astronomers hope to establish a more stable inertial frame of reference. Think of it as a fixed backdrop, against which they could then try to measure the much smaller movements of the globular clusters themselves using other observational techniques.
Makes sense.
In cases where there weren't suitable nearby Hipparcos stars, some researchers even had to rely on extremely distant objects like quasars and other galaxies to try and define an absolute reference frame.
Wow. That sounds like trying to measure the tiny movements of a small boat using landmarks on a distant continent.
A very fitting analogy.
Mm.
Despite these challenges, Hipparcos did lead to some advancements. Studies using its data helped us to better understand the orbits of 38 halo clusters and 4 inner galaxy clusters.
So some progress there.
Yeah, and one interesting finding was that these clusters appeared to have space velocities smaller than the escape velocity of the galactic bulge, the minimum speed needed to break free from its gravitational pull.
Meaning they were kind of stuck in the inner galaxy?
That's what it suggested, yeah, confined to the inner regions. But overall, the fundamental limitations in sensitivity meant we still lacked the detailed, precise measurements necessary for a real breakthrough in understanding the outer parts of the galaxy and its total mass.
Which perfectly sets the stage for the Gaia mission. So, when scientists were conceiving of Gaia, what were the key questions they specifically hoped it would answer about globular clusters?
Oh, the scientific wish list was quite extensive. Right at the top was getting a much, much more accurate determination of the total mass of our galaxy. That was huge.
The big one.
The big one, yeah.
Oh.
But going beyond that, they were hoping Gaia would provide crucial clues about the formation and evolution of the clusters themselves. For instance, being able to distinguish between those that formed in situ, right here within the Milky Way, and those that were accreted, brought in from smaller galaxies that merged with ours.
Ah, the origin story.
Exactly. They also wanted to investigate the effects of the Milky Way's gravitational tides on the clusters, how the galaxy stretches them,
Right.
as well as the internal physical processes occurring within them. The exciting possibility of discovering remnant streams of stars that had been torn away from the clusters was another major goal.
Finding those trails again.
Yep. And there were even more ambitious questions, such as whether globular clusters originally formed within their own small halos of dark matter, or if some might harbor intermediate mass black holes at their very centers.
So Gaia was designed to tackle everything from the Milky Way's grand structure down to the intricate details of these ancient star cities. Quite a job.
Absolutely. And the first real taste of its capabilities came with the second data release, DR2, in 2018.
Right. Let's delve into the findings from Helmy and her team. What did they uncover?
Well, the 2018 study by Helmy and her colleagues was a true turning point. Using the incredibly precise astrometry that's the measurement of their positions and motions from Gaia DR2, they examined the space motions of 75 globular clusters.
75, okay.
Now, While that might not sound like all of them, it represented about half of the known globular clusters in our galaxy, and they specifically focused on the ones relatively close to us, within about 12 to 13 kiloparsecs.
So the nearby ones first.
Exactly. And importantly, they also had measurements of their radial velocities, how fast they are moving towards or away from us, for 57 of these clusters.
And this represented a monumental leap forward in terms of the quality of the data itself, correct? Compared to Hipparcos.
Absolutely enormous. Night and day, really. Unlike Hipparcos, which couldn't resolve individual stars within globular clusters, Gaia could identify and measure thousands, even tens of thousands, of individual member stars in each cluster, extending all the way out to their tidal radiuses, the point beyond which the Milky Way's gravity starts to rip stars away.
Wow. Individual stars.
Yes. As a striking example, in NGC 104, also known as 47 Tucanae, which is the second closest globular cluster to us,
47 Tucanae. Yep.
they identified over 60,000 individual member stars.
60,000.
And the precision of these measurements is truly astounding. For 47 Tucanae, they determined a mean parallax, that tiny shift in its apparent position due to Earth's orbit of 0.1959 plus or minus 0.00002 milliarc seconds.
That sounds incredibly small.
It is. And from that incredibly small angle, they could calculate a distance of 501.05 plus or minus just 5 parsecs. That level of accuracy was simply unheard of before Gaia.
That's mind-boggling. Seriously precise. So what did these incredibly precise measurements reveal about the clusters themselves? Did they confirm old ideas or find new things?
Well, for one thing, the overall proper motions they calculated for each cluster, how the entire cluster is moving across our line of sight, were significantly larger by 1 or even 2 orders of magnitude than their parallaxes.
Meaning the motion measurement was really solid.
Exactly. It meant that the proper motion measurements were exceptionally robust and reliable. They were then able to precisely determine the location and the three-dimensional motion through space for all 75 of these clusters.
The full 3D picture.
Yes. And the sheer quality of the data, combined with the fact that Gaia's measurements are tied to a very stable, absolute reference frame, allowed them to clearly detect rotation within 5 of these globular clusters.
Rotation? You mean the entire cluster is spinning like a giant ball?
Exactly. 3 of these, NGC 104, NGC 5139, and NGC 7078, were already known or suspected to exhibit rotation.
Okay.
But Gaia's data revealed clear evidence of rotation in 2 additional clusters, NGC 5904 and NGC 6656. That was new.
Huh. So Gaia confirmed some and found new rotating ones? Cool.
Yeah. And they also observed other fascinating velocity structures within individual clusters. For example, NGC 32Val1 showed a distinct perspective contraction, which is a visual effect, like a compression, caused by its significant motion towards us combined with its relatively large parallax.
Ah, like things rushing towards you look squashed.
Sort of, yeah, an effect of perspective.
Yeah.
And in NGC 6397, a cluster believed to have undergone core collapse, they found indications of an expanding outer halo of stars.
It's as if Gaia gave us a completely new level of resolution, like zooming in on these ancient star systems.
That's a great way to put it.
But how did all this detailed information, the rotation, the expansion, help us better understand the Milky Way's overall mass? That was the big goal, right?
That's the critical next step. Helmy and her team took these incredibly precise positions and space motions and combined them with the most advanced models we have of the Milky Way's mass distribution.
Okay, feeding the data into the models.
Right. These sophisticated models take into account the mass of the central stellar bulge, the flat disks of stars and gas, and crucially, the dark matter halo, the invisible mass that makes up a large fraction of our galaxy.
Can't forget the dark matter.
Never. By feeding the highly accurate Gaia data into these models, they were able to trace the orbits of these 75 globular clusters backward in time over a period of 250 million years.
So they could essentially create a kind of time-lapse movie showing how these clusters have been moving around the galaxy, rewinding the clock.
In a sense, yes. And what was particularly remarkable was how consistent the predicted past orbits were across different models of the galaxy's mass, at least over these relatively short timescales, cosmically speaking.
Consistent. That's good.
Very good. This high level of predictability strongly suggests that we can now use these predictions of their future paths to search for the tidal tails of these clusters, the streams of stars that are gradually being pulled away by the galaxy's immense gravity as the clusters orbit.
Ah, finding more of those faint trails.
Exactly. Furthermore, by studying the orbits of more distant globular clusters with future data releases from Gaia, we'll gain a much deeper understanding of their relationship to the dwarf galaxies that currently surround the Milky Way.
It all ties together. The remnants of galaxies that were consumed long ago, the tidal tails of these ancient clusters. It's painting a much more dynamic and detailed picture of our galactic neighborhood.
Absolutely. And the potential for identifying the faint traces of long-gone accreted galaxies by carefully studying these Gaia-observed globular clusters is enormous.
Mhm.
Ultimately, the scientific expectation is that the complete Gaia dataset will allow us to determine the mass distribution of the Milky Way far out into the mysterious dark matter halo with an accuracy we've never had before.
That was one of the really big unknowns before, wasn't it? The true extent and shape of the dark matter halo.
Precisely. And in more technical terms, Gaia's data should finally allow us to resolve a long-standing degeneracy, a kind of fundamental confusion
Okay.
between the slope of the mass density profile of the halo, how the dark matter is spread out as you move away from the center, and what's known as the orbital anisotropy of the objects orbiting within it.
Orbital anisotropy.
Basically, how much their orbits are aligned or randomly oriented. Are they all going roughly the same way, or is it more like a swarm of bees? This unknown anisotropy has been a major obstacle in accurately pinning down our galaxy's total mass distribution.
I see. It confused the calculations.
Exactly. But the data from Gaia DR2 has already demonstrated that this anisotropy should soon become a directly observable quantity, not just something we have to guess at.
That's some seriously impressive scientific detective work. Resolving that confusion sounds key.
It is, and it's really worth emphasizing the sheer scale of the improvement. Compared to the information we had before Gaia, the uncertainties in these crucial measurements have been reduced by roughly a factor of 100.
100 times better.
Yeah. As Helmy and her colleagues concluded in their 2018 paper, the measurements for these 75 clusters are of outstanding quality, with the formal and systematic uncertainties being effectively negligible.
Negligible. Wow.
That's a very powerful statement about the impact of this mission.
It truly underscores the transformative power of a mission like Gaia. So just to recap, we've seen how studying the movements of globular clusters has been a long-standing goal in astronomy, kind of a holy grail.
In a long time, yes.
But Gaia has provided an incredible leap in precision. It allows us to measure individual stars within these ancient clusters and to trace their orbits through the galaxy with unprecedented accuracy. This is giving us a much clearer understanding of not only the Milky Way's total mass, but also how that mass is distributed, including the enigmatic dark matter halo.
Exactly. We're moving from having a somewhat blurry sketch to having, well, almost a high-definition image of our galactic home and its long history.
And it's all thanks to these ancient star clusters, acting as incredibly useful cosmic tracers.
It's a potent reminder of just how much we can learn by carefully and precisely observing the universe around us.
It definitely gives you a whole new appreciation for those faint, fuzzy blobs you might occasionally glimpse through a telescope. They're not just beautiful, they're actually telling us the ongoing story of our galaxy.
They really are cosmic historians.
So here's a final thought for you listening. Now that we're on the cusp of being able to measure the Milky Way's dark matter halo with far greater precision, what currently unknown aspects of the universe might this new knowledge unlock? What secrets are still hidden within that vast, unseen component of our galactic home, just waiting to be discovered?
Good question.
It's a universe that is still very much in the process of being explored.